3-SAT polynomial time CARP reduces to directed Hamiltonian cycle. So given an instance for 3-SAT, which is just a Boolean formula, we construct in polynomial time an instance of directed Hamiltonian cycle that has the property that it has a Hamiltonian cycle if and only if the Boolean formula was satisfiable. As always in these constructions, especially if you're dealing with two quite different problems, here 3-SAT and directed Hamiltonian cycle, you want to identify the crucial properties of these two problems. In 3-SAT, the crucial thing we have is we have variables that can take one of two values. So we have a variable x that can be true or false. And we somehow need to find a way to model this choice in directed Hamiltonian cycles. So we need to construct a graph where maybe there are two different options, and that these two options should correspond to setting some variable to true and some variable to false. And then we need to create this for each of the variables and connect all of this somehow. So how can we do this? Well, so one idea is the following. We create for each variable a line of vertices. And we create edges between these that are bidirectional. So we create an edge from a vertex to its neighbors and also an edge from its neighbor back. So we have an edge in both directions here. Now, if we want to visit all these vertices in one go, we have basically two choices. We can go from the very left end of this line and then move all the way to the very right end of that line. Or we can do it the other way around. So we can start at the right end of the line and move all the way to the left end of the line. What we cannot do, importantly, is that we cannot move partway through the line and then go back. So we cannot start at the left, go to the middle of the line, and then return to the left. The reason is that in Hamiltonian cycle, we have to visit each vertex exactly once. And in particular, we have to visit it at most once. And what I just described, like going to the middle and then back, would visit these vertices twice. So we need to construct such a line for each variable in our Boolean formula. So we have variables x1, x2, x3, and for each of these variables we construct such a line. And of course we need some ability to decide whether we want to start at the left end or the right end. So from some starting node, first we can go to the left end of this x1 line or the right end of that x1 line. And then we might be able to pass through that line to the other side. And then we have the line for x2. And no matter whether we end up at the left end of this x1 line or the right end of the x1 line, we should be able to get to the left end or the right end of the x2 line. So we create directed edges going from the left end of the x1 line to the left end of the x2 line, and to the right end of the x2 line. And we also include directed edges to go from the right end of the x1 line to the left end of the x2 line and to the right end of the x2 line. And then we repeat the whole process for x3 as well. And you can do this for as many variables as you need. And then at the very end, we have some like terminal node t, just for technicalities. And then we have to close the directed cycle somehow that we're trying to construct, so we can go from t to s. We include a directed edge from t to s. So far, this construction now is a directed graph. And this directed graph has the property that it has directed Hamiltonian cycles. And if you think about it, you will see that the number of directed Hamiltonian cycles that we have in this graph is 2 to the number of variables. So if our Boolean formula has n variables, then we would have 2 to the n different directed Hamiltonian cycles because we would have n lines. And for each line, we can decide independently of the others whether we want to go from left to right or right to left. But this is really the only choice we have, so there are no further directed cycles here. One thing that I didn't specify yet is how long these lines should be, and this really depends on the number of clauses that we have in our formula, and we will see why this is the case later. Suppose we have k clauses in our Boolean CNF formula, then we would need 3k plus 3 vertices on each line. So we've now modeled the choice we have in assigning truth values to the n variables in this directed graph corresponding to different Hamiltonian cycles. What's now left to do is to also model the clauses of our CNF formula in this graph in some way, and this should be done in such a way that we still have a directed Hamiltonian cycle in the end, if and only if all of these clauses are satisfiable simultaneously. We further extend the graph by including one additional vertex for each clause in the formula. And now what we do is we connect these extra vertices in a very specific way to the remaining graph. In particular, we allow you to visit that vertex in your directed Hamiltonian cycle if and only if you happen to traverse the correct line in the correct direction. So for example, if a clause contains the literal x1, then let's say we identify going from left to right with setting x1 to true and going from right to left with setting x1 to false. So then what you would want to do is you would want to take some vertex on this line and have a directed edge from that vertex to this clause vertex, and then have another directed edge from the clause vertex to the next vertex on the line, the vertex to the right of this. This is because x1 is not negated in the clause, so we want to be able to visit that vertex seamlessly when we go from left to right. On the other hand, say the second clause contains x1 negated, then we would want to be able to visit that clause vertex when we traverse this top line from the right to left. So what we would do is we would take two vertices and we would create a directed edge from the right vertex of this pair to the clause node, and then create a directed edge from the clause node to the left vertex of that pair. So this means if we go from right to left, we can seamlessly include this clause vertex into our cycle. But if we go from left to right, this is not possible because we would need to visit the clause from the right vertex of that pair. But then we wouldn't be able to go back to the line because the only way back is using the another directed edge, which leads us to the left vertex of the pair, which we've already visited previously. So we would visit that vertex twice, which is not allowed in a cycle. Of course, it's possible that maybe for clause 1, x1 is false, but x3 is true, and so therefore we can satisfy the clause in that way. So for each of the literals that appear in the clause, we add edges according to this rule. So in this case, for x3, for example, we would also create directed edges from this third line like this. This finishes our construction. Let's see if it works. If our formula has a satisfying assignment, then I can also find a Hamiltonian cycle in this graph. If a variable in the satisfying assignment is set to true, I will traverse the corresponding row in the graph completely from left to right. And if it's set to false, I traverse it in the opposite direction. If we do this, then for each clause, because each clause must have a true literal in it, there will be at least one row in which we are going in the correct direction, meaning in the direction that allows us to splice this closed node into our cycle. So if this is a satisfying assignment, then indeed we can splice in all the closed nodes into our tour and therefore get a correct directed Hamiltonian cycle that visits each vertex exactly once. For the opposite direction, suppose we have a directed Hamiltonian cycle in this graph. As I said, it's not possible to traverse a line partly and then return to the end that we came from. So we either have to go through all the way from left to right or all the way from right to left, possibly visiting some closed nodes in between. It's not possible to enter the closed node through some edge and then not leave the closed node through the sibling edge, but instead use some other edge that jumps completely to a different line. The reason why this doesn't work is because we would never be able to get back to the initial line. The directed edges only allows us to go from one line to the next at a time. We will not be able to go back before we have to return to the start vertex S. For this reason, the node that we visit just before we visit a closed node will be connected to the node that we visit directly after we leave that closed node. There will be a directed edge between them. And so we can remove this closed node from our path and just follow the new path using this directed edge for the nodes that we visit just before and just after the closed node. In this way, we can remove all the closed nodes and we are left with a simplified path on the remaining nodes of the graph, which just for each line goes from left to right or from right to left and then goes to the next line. And now we found our satisfying assignment for the formula. We just set a variable to true if the corresponding line is traversed from left to right, and we set it to false if it's traversed from right to left. And because the original directed Hamiltonian cycle we had did visit all of the closed nodes, it has to traverse at least one of the paths that correspond to the variables that appear in that clause in the correct direction. And therefore each clause is satisfied, and therefore the formula is satisfied. The construction is also simple and can be done in polynomial time. The total size of the graph is, well, we have one line for each variable. So if we have n variables, we have n lines. I said each line contains 3 times k plus 3 many vertices. If the formula has k clauses, so we have a total number of vertices of n times 3k plus 3 plus 2 for the starting vertex and the terminal vertex. And so this graph clearly also has polynomial size.